Okay, so in this videos, we're going to actually be doing some review. Back in Algebra 2, pre-calculus, you learned about sequences and series, and I just need to refresh your memories on this because this is going to be one of the ways we start transitioning to discussing series in terms of calculus. But there's not really going to be any calculus in what we're doing here. So first off, we need to talk about sequences. So a sequence is a list of numbers. So we're not adding, we're not subtracting. It is literally just a list of numbers, but they have to be written in an explicit order, meaning there's a rule that generates the next term of the sequence, and the terms need to be in a specific order. So an example of a sequence could be 1, 4, 9, 16, 25. And we're going to be mainly working with infinite sequences, but it could be finite. Um, but for the purposes of what we're doing, we're going to work with infinite because this is calculus. We study infinity. There are two ways we can define a sequence. Explicitly means we're being given an equation that tells me the nth term. So this we say a sub n, or this is the nth term of our sequence, and it's written in terms of n. So a sub n is equal to -1 to the n over n squared plus 1 says, okay, if I want the first number in the sequence, I plug 1 in for n. I get -1 over 1 squared plus 1, which is -1/2. If I want the second term in the sequence, I plug 2 in for n. If I want the third term, I plug 3 in for n, etc. The other is recursively, which is where I write a rule for the nth term based on the n minus first term. In other words, the term immediately preceding it. I could use other terms earlier on, but it's always based upon an earlier term. Commonly, it's going to be the one right in front of it. So here, if I say the first term is 4, the nth term means take the n minus first term plus 2. So take the term right before it and add 2. So if I'm starting with 4 to get the second term, take the first term plus 2, gives me 6. To get the third term, take the second term plus 2, gives me 8. To get the fourth term, take the third term plus 2, gives me 10, etc. We're going to be focusing on two types of sequences in this review. The first one being arithmetic. Arithmetic means that the rule that we're using is we're adding the exact same thing to get the next term. So we're always adding the same thing. So a good example of this would be the odd numbers, where I could say that my first term is 1, and then the thing I'm adding, which we call the common difference, and typically use D to represent, would be 2, because I'm going to add 2 every single time. So explicitly, I would say the nth term is take my first term, 1, plus the n minus 1 times my common difference of 2. So if I wanted the second term, I'd plug 2 in for 1, I'd get 3. My third term, plug 3 in for n, I get 4, or 5, and so on. Recursively, my nth term means that I take the term immediately before it and add 2. The other type of sequence is called geometric. And instead of adding the exact same thing every single time, we're going to multiply by the same thing every single time. So we're going to be dealing with what's known as a common ratio now, which we'll use to represent R. So if I think about exponential growth, where the population doubles, I could say that I'm starting with a term of 1, and if it's cell division, my common ratio is 2. So I'd have a sequence of 1, 2, 4, 8, 16, 32, etc. Explicitly, we take the first term times our common ratio raised to the n minus first power. So a sub n would equal my first term is 1 times my common ratio of 2 raised to the n minus first. Recursively, to find the nth term, I take the previous term times the common ratio. Now, with sequences, sequences will converge or diverge. If, as I go out an infinite number of terms in the sequence, the values of the sequence, the terms themselves, are approaching a real number, then my sequence converges. If, as I go out an infinite number of terms, the terms are not approaching a real number, either because they're bouncing around between different numbers, they're going off to one of the infinities, etc., then I would say the sequence diverges. And something that's really helpful for us is, especially when we deal with sequences where the terms alternate sign, plus, minus, and it's going to be something that you're going to see comes up later on, is we can simplify our work with a sequence a lot. If instead of saying, oh, let's see if the limit of the sequence terms approaches 0, instead, let's look and see if the limit of the absolute value of the terms approaches 0. Because if the absolute value of the terms approaches 0, the terms themselves approach 0. So in the examples here, I've got one that I don't really need the absolute values. I've got one where the absolute values are a big help. So I have the sequence a sub n is equal to n minus 1 over n. If I wanted to generate the terms, this is explicit, so I just start by plugging 1 in to begin with. So my sequence would start at 0, plug in 2, I get a half, plug in 3, plug in 4, plug in 5, etc. And I want to know if that sequence of terms approaches anything. Does it converge? To do that, I'm taking the limit as n goes to infinity of my terms, n minus 1 over n. Well, the limit of the top as n goes to infinity is approaching infinity. The limit of the bottom as n approaches infinity of n is infinity. So I have infinity over infinity. That's one of my indeterminate forms. I can use L'Hopital's rule. And I have the limit as n goes to infinity. Derivative of the top is 1. Derivative of the bottom is 1. And so this does converge. And it converges to 1. If I look at the second example here, again, it's given to us explicitly. I could generate the sequence. I plug 1 in for n. That's a negative 2 over 3. Plug in 2. That's a positive 3 over 6. Then a negative 4 over 11. And so on. To see if this is going to converge to anything, I'm going to do the limit as n approaches infinity. And I'm going to ignore the negatives sign going back and forth because I'm going to take advantage of this absolute value. So if I do the absolute value of my terms, the absolute value gets rid of my negative 1 to the n. So I'm looking at the limit as n goes to infinity of n plus 1 over n squared plus 2. I don't really need the absolute value signs at this step because n is a positive number, so the inside of that absolute value is positive automatically. I notice that the top is approaching 0, or approaching infinity. The bottom is approaching infinity. So I can do L'Hopital's rule. I have the limit as n goes to infinity of 1 over 2n. And since the top is 1 and the bottom is getting larger and larger and larger, this is approaching 0. So even though it's a little bit hard to tell by looking at the sequence of terms, this does converge to, oops, This does converge to 0. Now, one thing to be careful of with those absolute values, it only works if it converges to 0. If it doesn't converge to 0, I can't do this with the absolute values.